Good morning, good afternoon, or good evening, wherever you are located in the world, and welcome along to the AMETEK Solid-State Controls webinar on the capacitor and how it is used in UPS systems. It is September 17th, and I'm coming to you live from Houston, Texas. So the first question I always like to ask everybody is, can you hear me? So if you look on the right-hand side of your webinar panel, you will see a chat function. And if you can type in there whether you can hear me or not, it would be greatly appreciated. As always, I don't want to be talking to myself. I do that way more often than I'd like to admit. Thank you, Ben. Glad to see you here. Ben says he can hear us loud and clear. Very good. Okay, so while everybody else replies in the chat and signs into the webinar, I'll do a quick overview of who I am. My name is Craig Williams, and I'm the Senior Technical Manager for AMETEK Solid-State Controls, and I am located in the Stafford office, which is on the southwest side of Houston, Texas, in the USA. I have over 24 years in the industrial UPS industry, and I've worked with all of the major UPS and charger manufacturers internationally and local to the US. I've been with AMETEK Solid-State Controls. This is my 9th year now. I started off as a training manager, and I am now the Senior Technical Manager in charge of the service department. The platform we use is called Webinar Jam for our webinars, and there will be a lag of around about 30 seconds between me speaking and you hearing my voice, and that's because they have to do conversions and make sure that your iPhone or your Android phone or your Windows computer, whatever it is that you are watching the webinar on, the data has to be processed and converted, and that takes a little bit of time. So the reason I mention this is while I'm going through the webinar, if I come across a point and somebody puts a question in the Q&A function, I'm not going to see it until 30 seconds after I've gone over the point. So it gets kind of clunky. So what I ask that you do is you use the Q&A function. You'll see two tabs in your chat bar. You have chat and you have Q&A only. If you have a question, then please put it in the Q&A only tab. And then at the end of the webinar, I will go through all of the questions one by one and hopefully try and answer them. So feel free at any point during the presentation to put a question in the Q&A. Webinar Jam does have a panic button, which means if something goes wrong with the webinar and I see people in the chat saying that they can't hear me anymore or that the slides have stopped working, then I can press a panic button. Everybody will be moved to a different room and we will carry on as if nothing happened. Will the webinar be recorded is also another popular question. And as you can see, London has already put in the chat bar that the presentation will be provided after the webinar on our YouTube channel. Okay, and she's kindly put a link to our YouTube channel where all of the webinars that we've done historically are on that YouTube channel. You can share them. It's public access. You can do whatever you want with them. And the webinar should last around about 45 minutes to an hour. I'm very cognizant that you are busy people and you only have a certain amount of time in your day that you can watch things like this. So I do try and keep it to maximum of 1 hour, but it depends on how many questions we get at the end. Okay. So that's all the housework out of the way. So what is today's webinar going to discuss? Well, it's going to discuss the capacitor, and the learning outcomes are going to be, okay, understand what a capacitor is, understand what a capacitor does, how capacitors are used in basic electronics, and a couple of examples of how capacitors may be used inside a UPS system. Okay. So what is a capacitor? And I try and bring a different way of looking at things. When I was at university, my lecturers gave me lots of math and lots of information on how things worked. And in truth, that's not how my brain worked. What I wanted to know is what it does, how I can apply it, and somebody else can do the math for me. That's the way that I like to come at things. So there's not going to be much math in this. We're going to try and discuss a capacitor in an easy way that will hopefully give you a little bit of an aha moment, because it's how I learned to understand how a capacitor works. Now, if it doesn't help you, then hopefully it nudges you in the right direction. But that's what I'm trying to do. So in its most basic form, a capacitor is two parallel conductive plates. In other words, two parallel metal plates that are connected by a wire on either side. And then, as you can see, there is a gap in the middle. Okay. There has to be a gap in the middle, and that gap can be air, it can be a specific kind of material, but a dielectric layer is what it's usually called, but it's an insulator. In other words, there is no electrical connection between the two plates on either side. They are completely separated, okay? But they have to be very, very close together in order for the capacitor to do what it needs to do. So in its most basic form, this is a capacitor. And I forgot to put a slide in to tell you what the unit of measurement for the capacitor is, but it is the farad, okay? And the farad is extremely huge. It is a very, very large number, and it's very rare you're ever going to see a capacitor with a farad of capacitance. Usually we work with microfarads or picofarads, so very, very small amounts. Microfarad, I think, is 0.0000000. I can't get the other zero on because my screen's run out. One. I can't even do that. One there. So 1, 2, 3, 4, 5, 6 points is 1 microfarad. Okay. So that is what we are dealing with. And obviously, the larger surface area, the plates, and the closer together the plates are, the more capacitance you will have. The smaller the plates are and the larger the gap between the two plates, then the less capacitance you will have. And here is the first ever capacitor that was historically made, and it is called the Leyden jar. And basically, on the inside of the jar, there is some metal foil. And on the outside of the jar, there is some metal foil. And obviously, glass is the insulating material between those two layers of foil. And then, obviously, you have access to the material on the outside of the jar, and we'll call that the negative side of the capacitor. And then they put this rod through an insulating non-conductive top, and that goes through, and this chain rests on the inside metal material. And what you can do is you can put a positive charge with respect to this point here. So you can put a positive charge on the metal rod with respect to the outside, and then remove that charge, and then you can connect, let's say, just for ease, a lamp, and it will quickly discharge. So basically, the capacitor is a way to store electrical energy, although it's just for a very short period of time. So this is the very first original capacitor. It's called the Leyden jar. And thank you to How Stuff Works on the internet for having that picture that I could use. And you'll probably have seen a capacitor like this on a circuit board somewhere, or in Radio Shack when it was still in business. This is actually a ceramic capacitor. And this picture here shows you exactly what's going on inside that ceramic capacitor. And what you have is you have two metal electrodes that are connected by wires that then go down into the printed circuit board. And then the dielectric, or the insulator between the two plates in a ceramic capacitor, is a ceramic disc. Okay, and that's what keeps the plates separate and from touching each other, and provides just that very small gap between the two plates so you can derive its capacitance. Okay, so that is how a ceramic disc capacitor is made. Now, there are many other different types, polyester film, polycarbonate. There's just a lot of different types of capacitors that are made very similar to this. All they change usually is the dielectric in the middle. Sometimes they'll use plastic and different other materials. Okay. And then for an electrolytic capacitor, which you can see on the screen here, it's slightly different. And what they do is they have a roll of metal separated by two different layers. So first of all, on the outside layer, we have paper, and that's basically to give insulation between all of the rolls. Okay, so the paper acts as insulation. And then we have the positive foil. And in an electrolytic capacitor, it's very important to know that we have a positive and a negative. The ceramic capacitor was not non-polarity conscious. An electrolytic capacitor is polarity conscious. And it's because of this oxide layer that is formed on the positive foil. It actually acts as the anode. And this oxide layer is formed when you actually put voltage onto the capacitor for the first time. It's a very, very thin layer. It's an oxidization layer on the aluminum foil. And that thin layer is caused by the interaction with the tissue that's soaked in electrolyte. And what they also do is create an etched surface on the positive foil that creates more surface area, and that whole surface area becomes an oxide layer. Then, like I said, you have the tissue soaked in electrolyte, which separates the two layers, and then the negative foil, which is another layer of aluminum. And as you can see here, there's one layer of aluminum. Let's call that one the positive layer, and this layer here is the negative layer. You can see that there is some tissue soaked in electrolyte between the two layers, and then on the outside of the layer you have the paper separator that separates each of the rolls when it's rolled up. And then you have these two terminals here. Let's call this one positive, and let's call this one negative. But that is how an electrolytic capacitor is made. Okay. And obviously, the more rolls you can fit inside a capacitor, the bigger the surface area of the aluminum that you have, so the higher the capacitance of the capacitor. Okay, so that's why really big DC electric capacitors are quite large, and they have just a huge amount of surface area of aluminum foil that is separated by this electrolyte layer. And these are the symbols that you're going to come across on electrical drawings, schematics. So you have this one here and this one here. These are non-polarized capacitors. I don't know why some of them have this curved side here. In truth, there are some things that I need to know and some things I don't need to know. On this one, I didn't need to know. I just know that both of these are non-polarized capacitors. And then if they have a symbol on it, that means it is a polarized capacitor, and they are not interchangeable. A polarized capacitor has to be put into a circuit correctly with the correct polarity. Okay, a non-polarized capacitor can be put in either way. So now we're going to get into the analogy of what a capacitor does. And if you've seen any of my previous webinars when it comes to trying to to describe how an electric circuit works, I always default back to the water analogy because it is much easier for us to understand how water flows through a pipe, what it does when it passes a wheel, and all that kind of good stuff. So on the left-hand side, we have a pump. And on the right-hand side, we have a water wheel. Water wheel. Okay. So that is the two things that we have driving or being driven by the water. And then it's connected by pipes, and it's a closed circuit. Okay, no water escapes from this system, just like no electricity should escape from the wires. That would be a bad day. So that is the very basics of a simple electrical circuit. Okay, and if the pump drives clockwise, you can see that will cause the water to flow in a clockwise direction, and that will push down on the water wheel, and the water wheel will spin clockwise. But also do remember that water that is pushing through the water wheel does have to return and go back to the pump. It is a closed loop, just like every electrical circuit has to be a closed electrical circuit. So that is the basics of how the electric circuit works. And then obviously, if you spin the pump the other direction, the water gets forced this way and causes the wheel to spin in a different direction. And once again, the water has to return to the other side of the pump. So hopefully that gives you a basic understanding of a water analogy of an electrical circuit. And I like to use this description here where we use balls inside the pipe as well, because it gives you a better idea of actually what's happening inside. So you can see I've placed one red ball here and one red ball here, and you can see all throughout this pipe they are all touching each other. So it's a closed loop circuit, and if the motor spins in a clockwise direction, then this red ball pushes in that direction, which will push this red ball down. And then if you see the next slide, if we turn the pump around the other way, then you can see that the ball has moved back the way. Now, if I go between the two slides, you can see the ball moving backwards and forwards. So basically, if that pump was just moving very slightly one way, it would cause this red ball here to move very slightly in the same direction. So let me do it again. So you can see this red ball here, and it will go up and down as the pump moves. And basically what we're doing by doing that is we are creating AC, alternating current, because we're moving the ball in one direction and then the other, just like we would be moving the electrons in the wire. Okay, so what happens if we then put a capacitor in the circuit? Well, what we're going to do is we're going to put a capacitor in series with the circuit. So you can see here we have this black thing here. So I have to explain what my analogy is going to do. What this black line here is actually a rubber diaphragm. Okay, so it's mounted inside the pipe, and when something pushes against it, it has flexibility where it will bow that way, and if we push against it this way, it will bow that way. Okay, so it is flexible, but the important thing to remember is no fluid will flow through the diaphragm. It is a completely sealed system. All that happens is we can push on it in one direction, or we can push on it in a different direction. Okay, and that is a very good analogy for how a capacitor works in a series circuit. So once again, you can see if the pump is turning clockwise, the fluid will push against the capacitor. Okay, and what that will do is that will push against the fluid on the other side of the diaphragm and still allow this wheel to turn. But remember, no fluid is flowing through the diaphragm. Okay, it's only being pushed. Okay, and if we turn the motor the other way, fluid flows through the wheel up to this point here and pushes back on the diaphragm the other way, which pushes the electrons or the water back into the pump. So once again, no fluid is flowing on through the diaphragm. The pushing action against the diaphragm creates a reaction on the other side of the diaphragm. And it's easier to show with a ball. So once again, you can see this ball here, and you can see the black diaphragm with the ball there. And if I show you, if we go one way, so this is the motor going counterclockwise. So we're going this way. So these balls here are pushing against the diaphragm that way, which has moved this ball one step over. Okay, we've moved the ball a little bit that way. And then if we then, sorry, I always get the wrong direction. If we then go back, you can see that these balls here have moved one position. So let me leave these arrows here, and we can see that the balls are moving. So the balls are moving, but no balls are passing through the diaphragm. Hopefully you can understand what's going on there, because it's critical to know. So when you have a capacitor in a circuit, there is no current actually flowing through that capacitor, just like the ball is not passing through this diaphragm. It's critical to understand that's what's going on. So in an AC circuit, it's as if, in truth, the capacitor isn't there, because the diaphragm is still allowing the moving action of the balls in both directions. So once again, that way and that way, that way and that way. So the ball is moving, and therefore the wheel is turning with the action from the pump, or what it would be a generator or a power supply, but nothing is passing through the diaphragm. Okay. So, and the exact same thing is if I replace the pump with an AC power source, and I replace the water wheel with an electrical light bulb, and we have a sine wave which is pushing and pulling, just like the pump was spinning in one direction and the other. For the red portion of the waveform, we're pushing on the diaphragm this way, which pushes the electrons through the light bulb. But remember, no electrons are flowing through the capacitor. They're not flowing through the diaphragm. And then for the negative side, so let me, I'm not going to change my pen color, but for the negative side, then we are pushing this way through the light bulb, and we are pushing the diaphragm the other way. But no electrons are actually flowing through the capacitor. We're just pushing charge and discharging. So we're charging and discharging the capacitor as the AC waveform moves through its cycles, which comes to an important point. Okay, what happens if we put a DC power source with a capacitor in series with a light? Okay, well, what happens is if we close this switch here, then yes, we would push that diaphragm out that way for a very short period of time, but then it stops. Now it's stretched and it can't go any further. It is just stretched in one direction, and therefore we are now no longer pushing electrons on the other side. So the lamp will not light, and that's why we say DC cannot flow through a series capacitor, because we push on the diaphragm when that switch is closed, and then that's it. We're not changing the direction. Once it's pushed, then it can't release any more energy. So hopefully that lets you understand how a capacitor allows AC to pass through in a series circuit and prevents DC flowing through on a series circuit. Okay. Now then, that was a series circuit. Now we're going to have a capacitor in a parallel circuit. So what we've done is we've teed off this pipe here and we've created a parallel circuit in parallel with the wheel here. Okay. So remember it this way. Let's just say that the capacitor isn't there. We've got the pump. The wheel is going to spin regardless whether this capacitor is here or not. Okay. When we have AC, we're pushing and pulling on that wheel and it's going to move backwards and forwards. With this capacitor here, in truth, it's not really serving a purpose for us here, but I just wanted to let you know how it works in a parallel circuit. So if we go one way, you can see the arrows. Some of the current will actually flow through the water wheel, and then we will have a pushing action on this capacitor, on the diaphragm here. We will have a pushing action, but no water will actually flow through. Okay? And the same with a sine wave. For the positive half of the sine wave, obviously we will light the lamp because there is nothing to prevent the lamp being getting its current. But then we will also push down on this diaphragm. Okay? And it's easier to see what will happen if we use the balls again. So you can see we have this outer ring, which is going to have this ball, and this ball in it. And then this parallel circuit and the diaphragm is going to have this ball in it. Okay? So in normal, when we are spinning in this clockwise direction, the ball is going to move that way. This ball pushes down on the diaphragm, and this ball will actually move that way, as will this ball here move that way. But then, when the pump moves in the other direction, yes, this ball moves, and this ball moves, and the diaphragm will push this ball upwards as well. Okay? So the easier way that I like to look at it is, if we spin the pump clockwise, we are moving the balls that way, and down that way. But if the pump then stops, then this diaphragm will release its energy and it will push this ball up. Okay, this ball didn't move, this ball didn't move, but this ball did move, which will push on all of these other balls and push that ball down. So we would have spun that wheel for one step even after the pump had failed. That's what a parallel circuit can do. It can store some energy that can be released later at a different time. Okay? And it's the same with DC. Now, when we have a DC power supply and we close this switch, then we can light this lamp because there is nothing restricting the current to flow through that lamp. And then also some of the current or some of the electrons will push up against this diaphragm here for DC. So it will push for a short period of time. And then when we open that switch, what will happen is this diaphragm will then push back in the other direction. And with DC, there is actually a discharge curve. And if we know all of the parameters within the circuit, we will know how much energy will be pushed through this light, and the light will stay lit for a very short period of time, and then it will slowly dim and go out. And we know what this curve will look like based on what the resistance of the lamp is and what the capacitance of the capacitor is. So what we did in this circuit here is, if we go back here, we've closed this switch, we've stored some charge in this capacitor or in the diaphragm, and then when we open the switch, we allowing the release of that diaphragm, and it pushes energy through that way there until all the energy is gone down to this point here. So hopefully that explains how what they say is that a capacitor in parallel with a DC source will allow DC through and store some charge to be released if necessary. So a parallel capacitor with a DC source will allow DC to get through, okay? And if it was AC, some AC would go through the diaphragm and go backwards and forwards. So that's a lot of theory. Okay, balls moving in a pipe, water wheels, pumps, all that kind of good stuff. Hopefully it gives you an understanding using the diaphragm method of what the capacitor is actually doing. But how does that help us in the real world? I think that's what a lot of the teachers that I had and a lot of the lecturers that I had, they didn't really give real world applications for how that actually helps us. So here's the exact same circuit, and instead of a diaphragm and a pipe going down here, we now have a capacitor. And what we've done is, instead of having DC, we have a bridge rectifier here. And maybe you don't know. If you don't know how a bridge rectifier works, then please go and look at how it works. I've got some videos on it on the YouTube channel, or you can ask Grok, Google, whoever your search engine is or your AI model is, how does a full wave rectifier work? But basically what it does is it converts AC into this signal here. And this is called pulse DC or rectified DC, okay? This is actual DC voltage. But as you can see, it is changing in amplitude as we go through the cycle. So obviously down at this point here, it's 0. And up at this point here, that is its maximum value. That's its peak value. And then it changes between 0 and the max value all the way through. And in a lot of circuits, we don't want to have that changing DC voltage. We want steady DC voltage, just like a 9-volt battery. That a 9-volt battery would look like that. It would be flat. Excuse my very poor drawing. And that's what we're trying to do. We're trying to create DC direct current. And by direct current, we mean for each of these waveforms, we're pushing the current in one direction only. The current never moves in that direction. Okay? So what we can do is we can put a capacitor in parallel with this rectified DC voltage. And what's going to happen is, as you can see, this is the output waveform here, if we had an oscilloscope. So as we charge up here, that voltage is getting through to our loads. Okay, just like I showed in the previous circuit where we closed the switch, the DC passes through. But here's the interesting thing. Remember, this is a capacitor, so it's like that diaphragm. So we are starting to push down on that diaphragm. We're pushing in that direction. We're charging the capacitor. And once we get to this peak point here, okay, then it's like we've opened the switch, because the voltage starts to go down. So what the capacitor does is its diaphragm will push back in the other direction. It will release its charge, and it will start at this point here, and it will try and fill in the gap. And that's what we get at this point here. And then the sine wave starts up again here for this next portion. And once again, the diaphragm gets charged that way, or the capacitor gets charged up. And then that energy will be released again when the voltage starts to decline. And we get this point here. So a lot of people, when they see a capacitor inside a charger or a capacitor inside a UPS, when we're filtering the DC, because that's what the capacitor is doing, and we put a choke in it as well. But the capacitor is filling in the gaps. And what a lot of people don't understand is it's charging and discharging every single half cycle. So basically 120 times a second, that capacitor is charging and discharging. So it may just look like an inanimate plastic object inside your cabinet, but it is actually doing a huge amount of work. In fact, if you looked at the waveform out here, this portion here to this portion here is the capacitor working. And then if we looked at this point here, there's a sine wave. So the sine wave starts to work there. And then the sine wave stops working there. And then the capacitor works that point there. So you can see the actual power from the bridge rectifier is maybe on this 1/3 of the time, and then the capacitor is actually 2/3 of the time. So the capacitor is actually doing more work than the power coming, the AC voltage coming in. Now, obviously, the power gets transferred through the bridge into the capacitor, so the power is the same, but hopefully you understand what I'm trying to say, that the capacitor is doing a lot more work than you actually think it is inside your system. Okay? So another way we can start to understand how a capacitor can help us in a circuit inside a UPS or in any piece of electronics, okay? And we have to go back to the presentation I did last month and, you know, talk about a voltage divider or a potential divider to start off with. If you have a DC power supply that is connected to two identical resistors, okay, doesn't matter what the value are, then you create an identical voltage divider, and if you measured across both resistors, you will see 5 volts. It will split this 10 volts perfectly if these are exactly the same. Okay, that is what a voltage divider does. And to make it even more apparent, if we had a 1 ohm resistor here and a 9 ohm resistor here, you would have 1 ohm dropped across this resistor, and you would have the remaining 9 volts dropped across this resistor. Okay, so 1 volt dropped across there, 9 volts dropped across there, and 1 and 9 obviously makes 10 volts. So we have divided the power supply by putting 2 resistors in. Okay, well, interestingly, what happens if we replace one of those resistors with a capacitor? And what we've created by doing this is a timer circuit. And I'll go on to explain what's happening with this timer circuit. We want to know what the voltage across this capacitor is going to be at certain times throughout the circuit. So in this circuit here, the switch is open, so no power is flowing through the switch. So it's in its quiescent point. But if we then close this switch, the question is, what would we measure instantaneously across this capacitor? And it's very important to know, a completely discharged capacitor is an apparent short circuit to the circuit that it has been entered into. So you would, just for a very short moment, as soon as that switch is closed, you would measure 0 volts across the capacitor, and therefore you would measure 10 volts across that resistor. But then what starts to happen is the membrane or the capacitor starts to charge up, and it charges up in a controlled way. And it's a very easy way that we can calculate that value. So if you put an oscilloscope on the output of this circuit, what you would see is this waveform here. You would see the voltage across this capacitor start at 0, and then the capacitor would slowly charge up, it would get to this point here, which is basically 2/3 of its voltage, and then the remaining charge would charge up over time. That's a very small screen to look at, so I've enlarged it here, and basically it shows you what a time constant actually is. So here is the charge curve for a capacitor, any capacitor, okay? And we say that this T, or it's called tau in math, is when the capacitor charges up to 0.632 times the voltage applied to the capacitor, okay? So 1T is equal to the resistance times the capacitance. 2T would be 2 RC. 3T would be 3 RC, okay? So if we said that our RC network was a 10 kilo ohm resistor with a 100 microfarad capacitor, well, that would give us, this T would then equal 1 second. Because if we go to the next page, 10,000 times 0.0001, so 10K times 1 microfarad 100 microfarads, my apologies, is equal to 1. So what we're saying here, now that we have a 10K resistor and a 100 microfarad resistor, as soon as we close this switch here, we know that it is going to take 1 second to get to 0.632 times the input voltage, which for us is 10 volts. So it would take 1 second to get to 6.32 volts. Okay? And that is arbitrary. That is a calculation, just like Ohm's law, that cannot be refuted. It's just the way that it is. Much more clever people than me work this out. And I press the I believe button because nobody's proved them wrong yet. Okay? So, how that, I suppose you're all saying, okay, Craig, that kind of makes sense. How do you apply that to something? Well, what I'm going to do is progress you through an actual timing circuit. So what you can see here is we have a switch here, which switches this 10 volts through this wire, down through this resistor, and then charges this capacitor, okay? And then this switch here would discharge this capacitor through this resistor that way there, okay? Bear with me on this because in truth, this schematic diagram still doesn't make any real sense because it's not doing anything practical yet, but bear with me. So if we close this switch here, 10 volts would flow through here. Now we've got 5K and 5K, so that makes our 1K, just like we said in the previous schematic that we had. And then we still have a 100 microfarad capacitor here. So we know that this capacitor here is going to charge up to 6.32 volts in 1 second. Okay? We know that. And then what's going to happen is we then open that switch, and this has its 6.32 volts. If we then close this switch here, we allow that 6.32 to then discharge through that resistor down to ground. And then what you will get is, instead of the charge curve, what we're going to get is a discharge curve. It's going to go like that. And there's actually a calculation that you can use for a discharge curve as well. But I don't have time to go into that. Just press the I believe button that there is. So hopefully you understand what's going on there. We close this switch here, the capacitor charges up. Then we open this switch and close this switch, and that capacitor discharges. So we now have a circuit that we can charge and discharge the capacitor, but it's still done manually. We're using switches, so it still serves no real purpose in the world. And the reason that I've drawn the circuit like this is now, if we move on to the next slide, it's the exact same circuit, but now what we've got is we have what's called a 555 timer, which is probably one of the most common chips that you'll find in electronics. And basically, it's a way where we can utilize the action of a capacitor to create a timing circuit. Okay? So we've got to go through what some of these pins are doing. Now, remember, the basics are still here. We still have our 5K resistor there, our 5K resistor there, and our 100 microfarad capacitor there. We still have our 10 volts here, and we still have this switch here because we want to be able to switch the circuit on. Okay? And then pin 4 for this chip, it says it's a reset pin, and it says it must be high to work. In other words, it has to be at 10 volts to work. Okay, so if we close this switch here, that does become 10 volts and it will work. Okay, so that's pin 4. If the pin 4 is 0, we get nothing out of the circuit. If it's 10, if pin 4 is 10 volts, that is closed, then the circuit does what it needs to do. And we'll explain that in just a moment. Pin 8 is the power supply for the 555 timer. In other words, this output here is actually created by the power supply that goes into the chip. Okay, so we need a power supply in the chip to create this output. Then we have pin 7. This is the discharge pin, and basically what it's saying is pin 7 will actually be connected to ground. So this is ground here. So internally inside the timer circuit, this pin 7 will be connected to ground when the output is low. So at any of these points here, when the output is low, pin 7, basically it will discharge the capacitor. Okay, that's where we had that switch on the previous drawing. So the discharge pin is doing that inside this timer. Okay. Pin 6, and that's where that magic 2/3, the 0.623 voltage that we mentioned. Remember, 1 second, we're saying it will get to a 0.623 times 10 volts, which will be 6.23 volts. That's the threshold pin. And it says the output will go low when this pin here is more than 6.23 volts. Okay. Hopefully you're still following me. And then pin 2 is the trigger pin. The output goes high when that pin is less than 1/3 of the power supply. Okay, so remember, so what we're saying is pin 6 for the charge. Let me see if I can go back. So this charge graph here, that's what pin 6 is looking at. Okay, so as this capacitor charges up, T is equal to 1 second, we're going to get to 6.23 volts, and this output is going to go low once we get to 6.23 volts. Then what's going to happen is when it goes low, this pin here is going to be connected to ground, and we're going to discharge this way here. So instead of the charge curve, we're now going to have the discharge curve, and we're saying that when the voltage gets to, the voltage here gets to 1/3, which will be 3.3 volts of 10 volts, then the output is going to go high. And then that just continues over and over and over again. So what we can do is we can close this switch, turn the circuit on, and then what's going to happen is we're going to get a timer circuit output. And basically, it's going to take roughly 1 second for it using this 10K and 100 microfarad it's going to be like a 1 second space between each of the pulses in the grand scheme of things. Okay. And then what you can do, obviously I'm trying to think of real world situations where you would use this. Well, pretty much you are going to have inside your car, you're going to have a 555 timer in your car's ECU. And when you put your blinker on, it's going to turn this switch on. And then this output is going to be connected to the LED or the lamp in your flasher. And your flasher is going to flash at this timing ratio, whatever the manufacturer of the car chose. Okay. And then that is how the flasher circuit in most cars is working. And that flasher flashes at a speed only based on this resistor network and this capacitor network and this capacitor here. So if you change the capacitor, if you had access to it, and you could change the capacitor in your flasher circuit, you could make your flasher flash quicker, or you could make your flasher flash slower if you had access to it. So that is a good example of how a 555 timer works in an electronic circuit. And they're used all over the place inside UPSs. Basically, a long time ago when we had analog control boards, we could create an oscillator, which would then control the signal coming out of maybe a charger board or an inverter board to basically create a sine wave representation, or we could send signals to the SCRs based on an input as well. So there are many reasons why a 555 timer can be used. And no matter what 555 timer you have, it only works based upon the values that you choose for that resistor and capacitor network. So you have you can buy one chip and you can change these values, and it can flash slow, flash fast. It can go on for a long time and then off for a very short period of time. There are a huge amount of things that you can do with a 555 timer. So hopefully that gives you more of an understanding of what a capacitor does in an electronic circuit, what a capacitor does in a UPS. It's mostly used for filtering the DC inside a UPS to make the pulsating DC more of a steady state DC. Okay, so now we open it up and ask if there are any questions. So I'm going to go to the Q&A, and it seems we don't have any questions today. That means I must have explained very well how a capacitor worked, or I just confused the heck out of everybody on this webinar. Like I said, we all have different ways of learning, and using a rubber diaphragm just made sense to me on using a water analogy on how a capacitor works. And hopefully it triggered something in your brain that says, okay, that makes sense. If it didn't, then just do some more research and put it all together, and that would maybe help you find out more about how a capacitor works. So while I wait to see if there are any questions, I would like to thank everybody for joining us on this webinar. And for once in my life, I have finished on time. So I haven't taken up too much of your time. So that is good. We appreciate the fact that you took time out of your day to watch this. An hour in anybody's day is a considerable amount of time. And I hope that you found it worthwhile, and it was time well spent. You will be sent, because you did register for this webinar, you will be sent a survey by London in our marketing department asking if the webinar was any good. So obviously I recommend that you reply without saying it was awesome. But I think question 5 within the survey is what would you like me to discuss at our next webinar? And as I say on every webinar, I do read all of those surveys, and I look forward especially to hearing what you want me to discuss at the next webinar. So please let me know. It would be appreciated. And also, if you don't get that via email, London has put a link in the chat bar to show you. You can just click on that and you can fill out that survey. So we would appreciate that. Also, don't forget the YouTube channel link is still in the chat bar. So if you want to click on that and then bookmark that, then you will never lose access to all of our webinar series. Every single one has been recorded and put onto our YouTube video website. And definitely by tomorrow, London will have converted this webinar, and it will be on our YouTube site. Depending on how busy it is, she might get it done today, but we will see. But it will definitely be by tomorrow. And then, as always, sometimes you'll watch this webinar at a different point, or sometimes you'll watch this video sometime in the future on YouTube. If you want to contact us at AMETEK Solid State Controls, then, we're not AI, we are still human, so you can send us an email. London's going to put the email address in the chat bar in just a moment. You can use our contact form on our website, and those emails get sent directly to me so I can answer those questions. And then if you really want to go old school, give us a call. You do have to go through a menu tree, and all you have to do is choose service and then choose what region you're in. And then you will be directed to an actual human being, believe it or not, and they will answer your call. We have 24-hour service, so if it's after hours, our after hours call center will take that and route it to the on-call technical manager for that time, if it is urgent. If it's non-urgent, then we will reply the next day. So London, thank you very much. All of that information is in the chat bar now. So I don't see any questions, so I'm going to finish before 11 a.m. Central Time, which is a miracle in my eyes. I timed it to perfection. And if you do watch it again and you do come up with any other questions, or you want me to try and explain something in a different way, just let me know. I'll do what I can, because I know we all learn differently. And like I said, this was the way that I learned. So thank you very much for joining us. Appreciate you spending the time with us. Hopefully you got something out of it. Thanks for all of the good comments you've already put in the chat bar. I appreciate that. Jeff, Gavin, Mohammed, really appreciate you saying that you enjoyed it. It was a good presentation. And until next time, watch out for an email which will tell you what our next presentation will be. But I hopefully will speak to you in about 1 month's time. Thanks very much, everybody. Take care.